Let's prove exponential identities using the principle of mathematical induction. To prove exponential identities using the principle of mathematical induction, we need to understand how exponents work. Definitely, you're going to go back to how laws of exponents work, how to the processes involving simplifying exponential equations work, etc., etc. But still, we have the same three steps in proving these identities here under the principle of mathematical induction. Step one is still showing that the identity is true when n is equal to 1. Then in step two, we are going to show the expression when n is equal to k, and later on determine the identity that we are going to prove if n is equal to k plus 1. As I mentioned in the previous video, many references could also take this as step three or other arrangements of the steps, but nevertheless, our goal is to show that these are true. So for number one, its step one is by showing that n equal to 1 satisfies the identity. That would mean if you're going to substitute the value of n, which is 1 here, this should return to the first value of this series. Let's try. I have 2 to the power of 1 minus 1. That's actually 2 minus 1. And then the result is 1. This is now the same with the first term in this series. So it satisfies the first condition. As for the second condition, we need to show the expression when n equals k. So this identity could become 1 plus 2 squared plus 2 cubed plus dot plus 2. The exponent n will become k minus 1. And this should be equal to 2 to the power of k minus a term, not an exponent, of 1. This should be its form when n is equal to k. To show the expression that we are going to prove later, we just simply need to add another expression here when that explains another next value of the term when n is equal to k plus 1. So this will become 1 plus 2 squared plus 2 cubed plus dot plus the original 2k minus 1 and plus another expression here where k is actually k plus 1. And then you have here minus 1 still. We are going to add the same expression on the right hand side, which is actually originally 2 to the power of k minus 1. And we are going to add, as I mentioned, the same expression here. This is the expression that we are going to show later as true. So this is now the expression that we are going to manipulate later on. Specifically, we need to show that this expression could become the endpoint of the expression here when k is equal to 1. The point here is if we are going to change k here as k plus 1, this it actually becomes 2 to the k plus 1 minus 1. So we need to manipulate this expression here for step 3 that it should actually return to this expression here. So here's step 3. We need to show again this expression. You have 2k minus 1 plus the quantity 2 exponential 2 with exponent k plus 1 minus 1 will return to this expression. How? Let's try to simplify the exponent here. This would still become 2k minus 1 plus the expression, or the exponent rather, will become 1 minus 1. That's 2 to the power of k. This way, there are two terms with 2k right now. So we can treat them as one expression and say that there are 2 to the power of k. And then we have another term minus 1 here. What is the purpose for this? The purpose for this actually, again, is telling us that there are 2 to the power k expressions. And with this, the loss of exponent tells us that with this exponent as 1, we can combine it using multiplication law. And you will have here 2, 1 plus k minus 1. Or by simply arranging this with the variable first, you will have 2 to the power of k plus 1 minus an 1 here as a term, not an exponent. Let's see if this is actually the same as the expression earlier when we used the value of k as k plus 1. This is the expression, and this is the expression at the bottom. They are the same. Let me remove this. They are the same, and therefore, this is the proof that the statement here, or the identity here, is true. Let me have it here so that we could actually have more spaces for number 2. So the same thing will happen in number 2. We'll assume that is equal to 1. And then we are going to show if it's really true for the said expression or identity. And if it did, or if it will be, we are going to have n is equal to k, and then k plus 1 later on, to show which endpoints we are going to see as equality and manipulate the expression. So for number 2, we have this. So for step 1, we are going to have the value of n is equal to 1. Again, you substitute 1 here and see if it could return to the first term in this expression or side of the identity. So you will have 4. You'll have 4 to the power of 1 minus 1 over 3. That's 4 minus 1 over 3. That's 3 over 3. And this is actually 1. It satisfies the given identity now, since this returns to the first term of the left hand side. With that, we'll have our step 2. And step 2 is when n is equal to k. So we have here this given expression. We'll have 1 plus 4 squared plus 4 cubed plus dot 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 plus 4. The n will become k now, minus 1. And the other side will be having 4 to the power of k minus 1 all over 3. With this expression now, our next step is to get that identity that we would like to prove by adding another term, which is actually the next value to k, which is k plus 1. So what we're going to show is 1 plus 4 squared plus 4 cubed plus dot 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 plus 4 k minus 1. Okay, just like what happened here, we are going to add another expression where k is now k plus 1. So we have this expression here, 4 k plus 1 minus 1. This is what we're going to add on this side. And this should be equal to the same expression, 4k minus 1 all over 3 plus the same term that was added. So this is the item that we are going to manipulate, okay, and show later on that this could equal to an endpoint. And what is that endpoint? Again, the endpoint is when this value here is expressed as, the k is expressed as k plus 1. So let me write it here. So this would actually be k, 4 rather, k plus 1 minus 1 all over 3. This is our goal. Okay, we need to show that this expression will become that for our step 3. So let's manipulate this. You have 4 power of k minus 1 all over 3 plus the expression 4k plus 1 minus 1. By the way, it has minus 1 parentheses here, but nevertheless, it looks like that. So let's try to combine this first. So we have this expression. Let's have LCD 3. So we'll have here 4k minus 1 plus we have here all over 1 as we all know. So we'll have here 3 times 4 to the power of k. And since we have 1 minus 1, we'll have that expression. So to rearrange this, you have 4 to the power of k. You'll have plus 3 4 times 4, sorry, times 4 to the power of k minus 1 all over 3. Because for these two expressions here, it has a common factor of 4 to the power of k. So let's have that. We'll have here this expression here. We'll have this expression 4 to the power of k times common number factoring. What's left here is 1 because we factor that out. Plus, we factor that out, you will have 3. We have not entertained first or yet the final expression here. Let's just stand it as it is. Then you will have 4 to the power of k times 1 plus 3, which is 4, minus 1 all over 3. Lots of exponents, same basis, and we do know that it has exponent of 1 here. So this could actually be rewritten as 4k plus 1 minus 1 here all over 3. Do we have the same expression as what we are trying to prove? Look at the two expressions here, this and that. And since we have that already, this shows that the next expression with exponentiation here is an identity. This is how we show our proof for identities that involves exponentiation under the process of Principle of Mathematical Induction. Please do try to review this as part of your reference. Bye, everyone.